that yesterday. These problems are a little tedious to plug in the calculator, and there's a lot of room for error. And, you know, if we are only adding up things from 1 to 6, it's not a big deal, but if I tried to add up from 1 to 76, it's going to take a long time to write all these things out and punch them in the calculator, especially if I'm not just adding up something like 1 over x. What if I were adding up 3x to the 4th plus 5x cubed minus 6x squared plus 7x minus 1, and I wanted to do all the x's from 1 to 100? That would take forever. So there are shortcuts. That's what we're getting into today, the rules for summation. If I were you, I would probably take a highlighter or something and highlight this box, because you need to know these rules. Especially on test or quiz, you will want these shortcuts for helping you add things up. So the first rule of summation has to do with constants. And the same thing when we did limits or derivatives or even those antiderivatives that we were doing, constants or those coefficients just trail along. So if you have a coefficient, you can pull it out in front of your sum. So for instance, if I had like 3x and I wanted to add that up from 1 to 5, I could pull my 3 out, just add up my x's from 1 to 5, and then take my answer times 3. Okay, you don't have to include the 3 on every term. Second rule. If you have terms being added together, you can do the sum of each individually and add those sums together. So these rules should be kind of similar to the rules that we had with limits and derivatives. So if you remember those and you just recognize similarities, you're not really memorizing anything new right now. Okay, third thing. This is kind of one shortcut. If I have the sum from I equals 1 to n of a plus b sub I. Okay, for instance, if I said sum from 1 to 4 of 2 plus, let's just keep it simple and say x. Okay, if I were writing that out, I would have 2 plus 1 plus 2 plus 2 plus 2 plus 3 plus 2 plus 4, right? That 2 was a constant, and it didn't change. How many times did I end up adding it? 4. So, notice that was the number here. So if I'm adding from 1 to n, how many times will I add this a in here? N times. So you just have to do n times a, then plus the sum from 1 to n of that b sub I. So if you have a constant, you can just take it times the number of times you're adding. You don't have to actually write it down each time. All right, and the last one. This is kind of just a spin-off of the previous one. If I'm adding from 1 to n of 1, does this 1 change each time? No, so I'm just doing 1 plus 1 plus 1 plus 1. What's my answer going to equal? N. You just add it up n times. It's just 1 times n, which is n. Okay. So we need to extend this to help us out some more. One of the common formulas we will have is like an x to a power, I to the k power, which means you would have 1 to the power, 2 to the power, 3 to the power, so on, all the way up to whatever we're adding here. Now there are formulas for a lot of these. The ones that we are going to learn and that you need to know are the first three values. So something to the first, something to the second, something to the third. These will be formulas that you are expected to know. So grab that highlighter again and highlight these three. This is what we need to know. Okay. Do you want me to show you where they come from, or you just want me to give them to you? Just give them to you instead of trying to prove it for you?
Yeah.
Okay. So the first formula is n times n plus 1 over 2. Basically it comes from if you wrote out all of your numbers 1 plus 2 plus 3 all the way up to your n, you could essentially, here I'm going to end up proving it to you just by explaining it. It has to do with finding the patterns. Like you could group them, you know, if I did the first and the last, that's your 1 and your n, you get an n plus 1. Your second and previous, like n minus 1, you add them together, they get n plus 1. And essentially it's like adding all of those up. The I squared term, that formula starts out the same. It's n times n plus 1 times 2n plus 1 divided by 6. Again, if you're really interested in where these come from, I'm happy to show you. But if you're just going to zone out, then I probably just need to skip that. And the cube formula is n squared times n plus 1 squared over 4. So you have to know these three formulas. It will help us add things up, and I will intentionally give you ones that would take forever on your calculator just so you have to use the formula to add them up. Okay? So that's what we're going to practice now, using these formulas to simplify some problems. So I want to find the sum of part A, the first 10 positive integers. So that's easy enough. We could do 1 plus 2 plus 3 all the way up to 10. That's not a big thing, but we can use our formula to help. So we are adding from 1 to 10 of just the integer, just the I. So the formula, if you're just adding something to the first, you do n, what's my n here? 10, times n plus 1, which would be 11, divided by 2. 110 over 2. You should get 55 over. And this one you could certainly check if you added up those numbers. Part B, I want their squares. So that means I want the sum from 1 to 10 of I squared. So the squared formula is n, so 10, times n plus 1, which is 11, over, or times 2n plus 1. What would that be? 21, divided by 6. 385. Part C is their cubes. So we want sum from I equals 1 to 10 of I cubed. So I cubed is n squared, so 10 squared times n plus 1 squared, so times 11 squared, over 4. $3,025. we okay with those? Now we're going to use a combination of these formulas and the rules we wrote down to add up some polynomial functions. So I want the sum from 1 to 10 of 7i squared minus 5i. So this is where it starts to get annoying if you're trying to do it by hand. If you have to do 7 times 1 squared minus 5 times 1 plus 7 times 2 squared minus 5 times 2. It's a lot of button pushing on the calculator. If we use our formula, first of all, we know that we could do the sum of each thing separately. And we also talked about what would happen with those coefficients. They would come out in front. So really what you have to do is 7 times the sum from 1 to 10 of I squared minus 5 times the sum from 1 to 10 of I. So then we use our formulas. So the I squared is n, which was 10 again, times n plus 1, which is 11, times 2n plus 1, so 21, over 6, minus 5 times your sum for I, so n times n plus 1 over 2. On the test or quiz, unless the numbers are really easy to work with, I'd probably just tell you to set it up like this and let you stop there. Homework, you've got your calculator, you can go ahead and calculate this for me. What does it turn out to be? I don't have a calculator. And I think we can all agree that's certainly faster than just doing it by hand. Alright, keep doing them. Okay, so we can break this up. We'll do the I cubed minus 3 times the sum from 1 to 5 of I plus the sum from 1 to 5 of 2. So the I cubed formula, what's my n? 5. So it's n squared times n plus 1 squared, at least 6 squared, divided by 4, minus 3. Okay, so sum from 1 to 5 of I. So the formula for I is n times n plus 1 divided by 2. Plus, what's the formula for adding up this 2? 2 times n, so just 2 times 5. So we get 225 minus 45 plus 10, or 190. Why don't you guys try the next one on your own? See if you can get it. Good. So if you do this, you're going to add up 5 minus 2 times the sum of j, so you get 5 times 8 minus 2 times 8 times 9 over 2. So 40 minus 72 is negative 32. Alright, let's look at the next one. This is a little bit different because I have that square on the outside. What should I do? Boil it out first. Very good. So if we do that, write it twice in FOIL. So we'll end up doing 4 times the sum of a squared minus 4 times the sum of k plus the sum of 1. This line right here is kind of optional. You don't necessarily have to write that out. I'm just doing it to show you exactly what's going on. So the k squared term, so our squared formula is n times n plus 1 times 2n plus 1 over 6. Okay, the first, so n times n plus 1 over 2. And how do you add up that 1? Yeah, it's just 1 times 10 or 10. Okay. 1,330. So let's use this now. Going back to that first example yesterday, we did the over and under estimate. I want to use the formulas to help with that. So example 1 yesterday, our function was x squared on the interval 0 to 3. And we did it twice. We did it with 3 rectangles, or 5 and then 10 rectangles. Let's do the 10 rectangles one. So when we set that up, okay, we did for the over, the change in x, remember from yesterday we had 3/10. And then we had to add up how many pieces? 10 of them. So sum from 1 to 10. Okay, here's where we have to think a little bit. Because I don't just want to add up x squared, do I? Look back at your work from yesterday. When we did our overestimate, what was the first thing we plugged in? We started with 0.6. Wasn't it 0.3? We did 2 of them. We did it with 5 rectangles and 10. So we're looking at the 10 one. So the first number we plugged in was 0.3. And then 0.6, 0.9, and so forth. So we have to figure out how we would represent that. Okay. You're on the right track. You're close. When we plug this in, we're going to have to square it, right? So we have to end up doing that 3/10 or the 0.3 squared. But that's just the first one. and I have to do all 10 of these, right? So essentially, you have to do 3/10 times I squared. So 3/10 times 1 is 3/10. 3/10 times 2 was 6/10. 3/10 times 3 would be 9/10. Would that give us the numbers we had in there? So the hard part about this is you have to figure out how to write the formula for it. So if we simplify this, you would get a 9/100 I squared. What can you do with that 9/100? Comes out, so that gives me a 27/1000. So now we can use our I squared formula, so that's n times n plus 1 times 2n plus 1 over 6. And I got 10.395. Is that what we got yesterday for the overestimate with 10 rectangles? Now, was this shorter? Maybe, maybe not, because it took a little bit to come up with the formula. But if I were going to do like 50 rectangles, would this be faster? Absolutely. So if we only have a few, it's not that bad to plug them in. But if we have a lot, this would save us time. Let's talk about how we might do the underestimate. This one is a little bit different. Still taking it times 3/10, but when we did our underestimate, what was the first thing we plugged in? 0. Now we could do the same type of thing if we start our I at 0, but in the formulas that I gave you, all of those required our I to start at 1. So the shortcut formulas assume your I begins at 1. So it gets a little dangerous if we want to try starting it at 0. But what happened when we plugged in 0 here? It just gave us 0, didn't it? 0 squared was 0. So could I just not include that term at all since it's a 0 here? So that means I need to add up from 1 to 9. Because that 10th term was the first one, which was a 0. And then it's the same thing. So our n is 9. The next one is 10. 2n plus 1. 19 over 6. And that gives me 7.695, which is what we had yesterday. We will work more on this. At this point, I'm not expecting you to use these formulas to find your over and under approximations. We're still doing those just by writing it out. But I just wanted to show you how this relates to what we were doing yesterday. Last example for the day. Ultimately, if we want to find the true area, we know that the number of rectangles has to head to infinity. Right? So that's where we're going with this. So I just wanted to practice one limit problem with you, and we will end up doing some more later. So if I wanted to find the limit as n goes to infinity of 1 plus 2 plus 3 plus so on, all the way up to n over n squared. This looks a little daunting right now. If I want to try to work this, when you see that, what is that? What does that mean? Isn't that the sum from 1 to n of just your I? So this thing I highlighted in yellow, couldn't that be written with the summation formula? It's adding up just 1, 2, 3. And don't we have a formula for what that adds up to? That we said that turns into n times n plus 1 over 2. Okay, we have to clean this up. This is like n squared over 1, so we know we could flip and multiply. What happens then? Cancel on n. So we have n plus 1 over 2n. Okay, if I just plug in infinity, I have infinity over infinity. What am I going to do? L'Hopital's would work. There's several options here, so L'Hopital's is great. That's probably the most recent thing that we've done. So that's the derivative of the top over the derivative of the bottom. Derivative of the top is 1. Derivative of the bottom is 2. So this equals 1/2. All right. Questions there? Today's assignment is another handout which has been posted on Classroom, so you have time to start that now.